now comes application that's very simple, but something that's very, very important. So we will look at the definition of a class of systems which satisfy a property called causality. Okay, remember we defined causality for a sequence. A causal sequence starts at n equal to 0 and goes towards infinity. It does not have any negative values. So what is, when it comes to a discrete time system, what is causality? So a discrete time system, y of n equal to t of x of n. Okay, we did not necessarily make it assume it to be linear time invariant, but basically, but this is a transformation, is considered to be causal if for every choice of n naught, every choice of n naught is an integer, the output sequence that is y of n naught, the output y of n naught depends only on the input sequence, at time n naught or earlier than n naught. Okay. So on the input sequence values x of n naught, that is current time input, x of n naught minus 1, x of n naught minus 2 dot dot dot. It can be all the way to infinity. Okay. So it depends on, so y of n naught, you can say, depends on x of n where n less than or equal to n naught. Okay, that's it. So basically the output at any time instant depends only on the current input and past inputs, not on any future inputs. Okay. Now I want you to look at this particular example. This is called an averaging filter. An averaging filter takes a few samples, adds them together and divides by the total number of samples. So this is a very simple operation that we use in discrete time signal processing. So y of n is equal to 1/3 of x of n minus 1, x of n plus 1. Okay. Obviously this is not causal. That was not the intent. Okay, so straight away, you wrote down the definition and then you wrote down a violation of it. But that was not the purpose. Is this system linear? Okay, x1, if I scale by a times x1, will the output scale? Of course. It will be a times x of n minus 1 plus a times x of n plus a times x of n plus 1, obviously output will scale. So scaling straightforward. Scaling, it will satisfy. Then superposition or additivity, let me call that as additivity. You add two signals, you will find that you can verify that there is no problem, additivity also will be satisfied. And is it time invariant? Time invariant, no matter where which index you give it, it will take the current sample, one past, one future. Okay, so basically wherever you go, it will produce if the input is delayed, output will also be delayed. So time invariant, you can verify, the answer is yes. The combination of these two things means that this is LTI, means this must have an impulse response. This must have an impulse response. The question that I am going to ask you is, what is the impulse response of an averaging filter? It is an LTI system. Because it is an LTI system, it should have an impulse response. So let us look at it and write down y of n will be equal to summation, okay, k equal to minus infinity to infinity. I am going to write it with the flipping of the input sequence. Okay, it is going to be x of k, x of n minus k. okay, because both forms are fine. So this will be equal to h of 0 times x of n, h of 1 times x of n minus 1, h of minus 1 times x of n plus 1. Okay. So if I were to ask you to write down the sequence h of n, you will then say it is equal to 1 by 3, 1 by 3, 1 by 3, 3 coefficients of 1 by 3. The origin h of 0 is in the middle. There is one tap to the left, one tap to the right. All of them are equal to 1 by 3. So basically, this is the impulse response. Okay. Now comes, if you have understood this, then you should be able to now expand this. So the averaging filter, the most general form of the averaging filter, okay, it is called the moving average filter, MA filter. Okay, this is another name, again useful for you to know. This is the generalized averaging filter, is called the moving average filter. This is given by a averaging over not 3 samples, but any number of samples you can say. So this is equal to summation k equal to minus m1 to m2 x of n minus k divided by 1 over n. 1 over n means how, if you added 20 samples, you divide by 20, divide by 20. Okay. So what you find is that if you write down the expression here, here also you will get h of 0 times, wait a minute, did I make a mistake? Okay, no, okay. h of 0 times x of n, h of n, I am trying to get the impulse response, h of 1 times x of n minus 1, there is a 1 over n for all of these guys. So, dot 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 plus h of minus 1 times x of n plus 1. Okay. Now, how many past samples are present here? N minus 1, n minus 2, n minus 3, all the way up to n minus m2. So, h of m2 x of n minus m2. Okay, these are all past samples. Where are the future samples coming from? Future samples are coming from the negative values of k. K equal to minus 1 is n plus 1. So, you go all the way to h of minus m1, this will be equal to x of n plus m1. Okay. Now look at it. If I have an impulse response, LTI system, impulse response is present, and I do not want, so this expression is not necessarily for an averaging filter, this is for any, so this is a summation h of k x of n minus k, k going from minus infinity to infinity. K going from minus infinity to infinity, general, we can also relate it to the averaging filter, but general. Now, when do you start getting future samples, your current output depending on future samples? If you have a h of minus 1, you have a h of minus 2, you have a h of minus m1. Okay. Now, look at the impulse response, where will these occur? This is 0, this is h of 0. At time 1, this is h of 1, h of 2, I have h of minus 1, h of minus 2, and so on. Okay. Now, these are the terms that are bringing in the future samples. These are bringing in the future inputs, because when you do the convolution, they flip around, they bring you the future values of input. Okay, these bring the past values, and h of 0 gives you the current value, right? This is the one that gives you the scaling of the current input, the past values of input. Okay. Simple question. If I tell you, give me a condition for an LTI system not to depend on future samples. Condition. Okay, you will say h of n equal to 0 for n less than k, right? Minus 1, minus 2, minus 3. If all of them are 0, then there is no dependence. So the bottom line completely goes away. What you have is only the top line, which is starting from x of n minus 1, x of n minus 2. So if this is a condition, what sort of sequence is this? It is 0 for all negative values, sorry, n less than 0, sorry, n less than 0. Okay. So such a sequence is called a causal sequence. Okay. If your impulse response, unit sample response is a causal sequence, then it is guaranteed that your LTI system, which is represented by this impulse response, will also be causal. By definition of causal, we mean that it depends only on only on past samples of the input, not on future samples of the input. Okay. So now this moving average filter is non-causal. Non-causal. How do you convert it to causal? Convert to a causal filter. Okay, two things. One is you look at the impulse response. Okay, the impulse response is h of n is equal to 1 over n. There is a scale factor for all of them. 0, 0, 0. There is a 1 here at the middle. This is the origin. Then you have all the positive samples. They are all equal to 1. How many of them are there? There is total of m2 of them, basically the positive side. Okay. Then on the negative side, we have 1 valued samples all the way up to minus m1. After that, there are zeros. This is the impulse response of this moving average filter, and because it is a non-causal sequence, because you basically have non-zeros on both sides, this is a non-causal sequence, and therefore, if I want to make it causal, then what do? I say, okay, ignore these samples. Start from n equal to 0 onwards. So then what will be the moving average? Y of n will be equal to, k will not start at minus m1, it will start at 0, it will go up to m2, x of n minus k, and this will be 1 over m2 plus 1, total of samples will be m2. This is also a moving average filter. This can also do the same type of computation as, but this is a causal version. This is a causal version. It is a causal moving average filter. It does not depend on future samples, only takes into account the past values of the samples that are present. Okay. So now what we find is that we are going to be dealing with a class of systems called the linear time invariant systems. These are systems that are always characterized by the impulse response. So first we started out by saying, okay, how do I make sure that the system is causal? Condition on causality. We will show now that if you want to impose conditions of stability, again go back to the impulse response. If you want to, in many of the properties of a discrete time system then depend on the impulse response of the system. So we find that we now have a very powerful tool for an LTI system. Linear time invariant systems are characterized by the impulse response, and by looking at the impulse response we can say a system is causal, whether it is stable, lot of things we can study. So what we would like to do is spend a little more time trying to define the properties of a LTI system as represented by the impulse response. Once we have that in place, then we have fully characterized and understood how to work with discrete time systems in the time domain. Okay, so basically I want you to think about the whole aspect of impulse response. What does it mean to be linear, time invariant? How did we get the expressions for the impulse response? What is the input-output relationship? What is convolution? How do I compute convolution? If you can review all of these things, then we can quickly build on this to complete the rest of the discussion as far as linear time invariant systems are concerned. Okay, let me stop here. I hope that you'll be able to review the concepts that we have covered in today's class, look at the examples, try out the exercises that we have given. Any doubts or questions, please feel free to ask, and then we will build on that. So in the next session, we will be completing our discussion on discrete time systems, and then we will be starting to look at how do we represent discrete time signals and discrete time systems in the frequency domain or in the Fourier domain. So that is our next step. Again, a very powerful tool for discrete time signal processing. Encourage you to keep abreast with the class and look at all of the worked examples and the concepts that we have given. Also try out the assignments, and then we will be in a good position to start the next unit of study. Thank you.